Mucho gusto. Me llamo David Malan. Hablo un poco español, but this will be in English, if that's okay, as this morning. But so nice to see some familiar faces and some new ones as well. As Jose said, we thought we'd give you an introduction to computer science, the goal of which is to empower you to have more technical conversations, perhaps with those students who are taking Jose's class right now, or those of you who are first years who might like to take Jose's class next semester or beyond. Please feel free to join us in CS50 and INCAE. Computer science is something that's unfamiliar to a lot of people. For instance, what is computer science? Anyone who's not in Jose's class? What is computer science?
Are we going to have to cold call people?
Yeah, I see no one's put up, very few people have put up their name tags in this one, but that's okay. ¿Qué es la informática? Anyone at all? Anyone at all? So, all right, someone, how about this? From Jose's class, what is computer science? Yes, please. Okay.
For example, computers don't speak the same languages that we do.
Okay.
You know, they work basically just with ones and zeros. So computer science is mostly a way to be able to program computers to do what we want.
Okay.
So we have to translate from our languages to the languages computers do.
Good. I really like that. So it's the study, it's getting computers to do what we want them to do, and more generally, it's the study of information and the processes around information that allow you to actually solve problems. And frankly, this was not clear to me when I first was able to study computer science way back in high school even. In la escuela secundaria, I did not study computer science because I thought it was only about programming, and it seemed very antisocial, and everyone's heads were down in the computer lab, and they seemed very focused only on the keyboard. But really, it wasn't until college, when I took a course called CS50, that I discovered that it really is more generally about problem solving. And what's exciting about computer science is that it's not just useful within the domain of computer science and analyzing data and information, but it really is something that you can bring back to your own world, whether that's in the physical sciences, natural sciences, arts, humanities, business, or the like, because it's really all about teaching you computational thinking. It cleans up your thinking process. It helps you think more logically. It helps you express yourself more precisely, more correctly, and as such, it just makes you a much better communicator and ultimately decision maker. And so with that said, let's start really at the beginning. What does it mean to think computationally? Well, it means to think methodically, more carefully, or as we'll see, more algorithmically, so to speak. And what does it mean to solve a problem? Well, I'd propose that it really is just this. Any problem in the world just has some input, the problem that you want to solve, and you want some solution, so we'll call that the output. And in between here is some kind of process, some kind of problem-solving mechanism that actually gets the job done. But it's pretty fair to say that this is computer science, at least at a very high level. But before we can discuss inputs and outputs, we, like a computer scientist, need to decide how to represent information. After all, at the end of the day, our computers, our phones only have, say, electricity. So we really all need to agree in advance how we somehow use electricity to represent inputs and outputs. And it's kind of funny that I just counted the two ingredients to this problem. How might we represent information if we're just counting information, the number of people in the room? Well, 1, 2, 3, 4, 5, or I could count higher certainly if I used hash marks, 1, 2, 3, 4, 5, 6, and so forth. And so that process has a name. It's called unary notation. Uno implying one, and that's just because you have one single mark or one type of digit, a finger, via which you can count people. So just a casual warm-up exercise, because there's a lot of folks who obviously don't know much about computer science. We would call you back home those less comfortable, and that's totally fine. That's the largest demographic of students taking CS50 back home. How high can I count on one hand? I hear 5. 6, okay. 6 is not right, but it is not 5. It's not 5. You're all wrong somehow. Well, why is that? Well, odds are, if you, like me, you start counting pretty reasonably, like 1, 2, 3, 4, 5. OK, now we're out of fingers unless we start using the second hand. So 5 would seem to be the highest. But that's because I didn't really think very hard about this problem and represent the information as efficiently, as optimally as I might be able to. Right? I'm just putting my fingers up or down, but I'm really taking I'm not even taking into account the order in which I'm raising or lowering my fingers. What if instead this still represents 0? I've not counted any 1 yet. But what if I do this is 1, and then maybe this is 2, and then this is 3, And then if we keep counting, it's slightly offensive in some cultures. This is 4. This is then 5. This is then 6. This is now 7. So even if you didn't quite follow the exact pattern I was doing, it was obviously not as simple as 1, 2, 3, 4, 5. I was instead kind of permuting them in different ways by raising and lowering them, thereby making a pattern out of them. And so in that case, it actually is significant if my finger is up or it's down. That is, there's 2 states my finger can be in. It's not just that there's a hash mark there or not. My finger is either up or down proactively. And that's called binary notation, bi implying 2. And that's because each of my fingers can either be down or up. Or we might call this off or on, or 0 or 1. But more on that in just a moment. So in other words, I can actually count much higher than 5 with 5 fingers. Does anyone know or want to do the math? How high can I count? Yeah.
31?
It's 31. It's very painful to count to 31 on your 5 human fingers because I don't think I can arrange my fingers quite cleanly enough to do that. But there are indeed 32 total patterns of fingers up and down on just one hand. If I start at 0 and I go up to all 5, there's 32 total. But if this is 0 and this is all up, then if I've got 32 possibilities, I can count from 0 to 31, it turns out. But more on that in just a little bit. So that's a lot. And that suggests that with a little bit more thought and a little bit more cleverness as to how a computer scientist represents information, you can pack a lot more information into very limited space. So how do we get, though, from unary to binary to computers? Well, at the end of the day, you probably all know or have heard that computers only understand binary, zeros and ones. So what does that really mean? Well, it turns out that computers, even though they might seem pretty sophisticated, they're pretty dumb devices, right? They only, first of all, do what we tell them to do. And that's the power, as Priscilla notes, of getting a computer to do something for you. But moreover, they only take one simple input. They take like electricity from the wall or maybe from your battery. And even if you've not studied electricity, it's electrons flowing in or out of the device, somehow powering the device. That's the only physical input. And so how perfect is it that there's a way to represent information by either putting a finger down or up or off or on that is 2 different states? Because you can represent 2 states really easily. For instance, my laptop right now is on, and thankfully it has battery. Now it would be potentially off because it's not plugged in. On, electricity is flowing, or off. So why is this germane? Well, a computer, it turns out, can represent information just by storing or not storing electricity. And that's powerful because you can somehow use electricity either on or off and represent, it turns out, different numbers. But what are those numbers going to be? Well, consider this. Even if you've never, well, let me ask a question first. How many of you can speak binary or understand binary? All right, Priscilla and a few other people. OK, so most people not. But it turns out, give me like 2 minutes, and everyone in this room will be able to. Why? Well, first let's start where we all started as kids. If you saw this on the board, this is, of course, what number? Yeah, well, 123, right? It's all very intuitive to us. But why? Really, all I did was draw 3 symbols on the board. I kind of went like this, and then this kind of curvy stroke, and then a slightly more curvy stroke, and drew these symbols on the board. But you all sort of instinctively assigned meaning to each of these symbols, and quickly, mathematically, got to 123. But why is that? Well, if you're like me in the US, I grew up learning that this is kind of the ones place, or the ones column. This is the tens place, or the tens column. This is the hundreds place, or the hundreds column, and then so forth. You keep multiplying by 10. And so the reason that 1, 2, 3 is 123 is because this is technically 100 times 1, and this is 10 times 2, and this is 1 times 3. That, of course, is 100 plus 20 plus 3. And this, of course, is 123. Now, this might seem like circular logic because I've literally written down the same thing. But now we've ascribed meaning to the positions of each of those symbols on the board. Now, what are these places really representing? Not to get too technical, but they're just powers of 10, right? The ones place is technically 10 to the 0, because 10 to the 0 is 1. The next place is actually 10 to the 1, and 10 to the 1 is 10. This is, of course, 10 squared, or 10 to the 2, and that gives you 100. And so 10 to the 3, 10 to the 4, 10 to the 5. These are just powers of 10. So a computer, and most of you a moment ago claimed not to speak binary, a computer is fundamentally really the same exact thing, except each of the places is not a power of 10. It's probably a power of 2 instead, right? We humans sort of naturally these days speak decimal, dec meaning 10, and that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Computer, turns out, speaks binary, and by convention, a computer only understands 0 and 1. And that might seem very limiting at first glance, but if this is the 1's place now, this is the 2's place, this is the 4's place, then 8, 16, 32. We can represent the exact same numbers, just with different patterns. But now the symbols I can draw are not 0 through 9, they're 0 through 1. So a little more limiting, but that's OK because the columns will allow me to do the same kind of math. So for instance, given this logic, if the only two things I can write with this chalk is a 0 or a 1, how do we represent in binary, that is zeros and ones only, the number we humans know as 0? Yeah. Yeah, so 0, 0, 0, it's kind of it's trivial. Why? Well, just 4 times 0 plus 2 times 0 plus 1 times 0 is still 0. So that one's not that interesting. How would we represent the number we humans know in decimal as 1? 0, 0, 1, yeah, so 0, 0, 1. And this is where it might get a little tricky for a moment. How about 2? Yeah, 0, 1, 0. And this is where now we see the connection to what I was doing with my fingers. I didn't go 0, 1, 2. The second time I went 0, 1, 2, thereby changing my finger from like a 1 to a 0 and a 0 to a 1 to give me this pattern. And of course, if you want to represent 3, it's going to be, yeah, 0, 1, 1. And now, how about 7? Yeah, 1, 1, 1, right? Because that's 4 times 1 plus 2 times 1 plus 1 times 1. So 4 plus 2 plus 1 is 7. And then maybe trick question, how do I represent 8? Yeah, we need another placeholder. And that's fine. You know, if we were on a piece of paper or a board, I can, of course, just write a 1 here. And then these, of course, now need to become zeros because implicit to the left here was going to be the 8's place, even though I don't need to write it from the get-go. But there's now a limitation. Computers, of course, are physical devices. And even if you have the fanciest of Macs or PCs, like you only have so much room in that computer. You only have so much memory, so much hardware. So it's certainly finite. And so let's actually dive down into what's inside of a computer such that you can actually represent the number 7 or 8 or anything in between using an actual computer. Well, it turns out that inside of a computer are, in simple form, just like lots of tiny little light bulbs, or more specifically, little switches that can be turned on and off. And those switches, when turned on and off, either allow you to store a little bit of electricity that came from the wall or the battery, or allow it to dissipate and go away. So those switches are called transistors, if you've heard the term. Transistor is just a tiny little microscopic switch. And CPUs these days, central processing units, the brains inside of a computer, the Intel inside hardware, has millions of these tiny little switches. But for the moment, I only have 3 of these switches. And so I claim that the number I'm currently representing with these 3 light bulbs is what number if they're all off? 0. So if you shrunk these light bulbs down, put them into your phone or computer, that's effectively, that was very dramatic with all the chalk, that's effectively how your computer would store 0. And if you wanted to store the number 1, well, you might just turn one of the transistors on, store a little bit of electricity, so now the computer recognizes this pattern of electricity. If I want to represent 2, do I want to just do this? No, so this should go off because this is the 1's column, 2's column, 4's column. So this is 2. This, of course, is 3. 4 is, you do this one here. So 4, this goes off, off. That's 4. 5, all the way over here. OK, 6. Middle, yep. And finally, 7. And now you see the physical problem. What if you want to represent 8? Well, all of us would have just carried the 1, so to speak, just as I did on the board. So OK, that's a 0, that's a 0, that's a 0. And damn, like we're now out of space. Unless, of course, thankfully, the team brought another light bulb. And now you have more memory, right? And so herein lies kind of the origins of why you run out of memory sometimes. And what it means to run out of memory just means you can't count as high, or you can't store, for instance, as many files in your computer's memory at once, or you can't load as many programs at once, because at some point you do run out of physical space. But it really just boils down to these very simple primitives. So literally everything inside of your computer ultimately boils down to zeros and ones, tiny little switches, if you will, those transistors that just store patterns of electricity thereby representing values. And without getting ahead of ourselves, if you were to study a hardware class in computer science and really become an electrical engineer, you would also explore the reality that when you have an Intel CPU, Intel is inside, not only does that CPU know how to store information, it also knows how to perform certain operations, addition, subtraction, moving values from this location in memory over here or vice versa. And that's what a CPU really does. It just manipulates these zeros and ones, moves them around, adds them together, and so forth. But for now, let's leverage a principle in computer science that's known as abstraction. And abstraction is just this general technique whereby you take a very simple, if like boring idea, and we just all agree, OK, I get it. I understand that computers can count to 7 or to 8 or to higher, but I don't really care here on out how they do it, right? Certainly in the business world, it's rare that you're going to need to, make any arguments in binary, but that's fine. We can abstract on top of this and just stipulate computers can count as high as they want so long as they have enough memory. There's a way of doing that. But how do we represent other pieces of information, right? Computers don't just do math. They don't just run Excel and calculators. They have word processing programs. They have spreadsheets, PowerPoint tools. So there's words and letters. So does anyone want to wager a guess at how a computer can represent not numbers, but rather letters of the alphabet? Jaime?
In the case of the letters, you can deal with it using the ASCII table, for example.
ASCII table. OK, so that's a loaded answer. What do you mean by ASCII table?
ASCII table is I don't know, a chart which shows you which is the value of one letter with numbers.
Yeah.
With decimal numbers, but you have to change it in binary. Well, the computer changes it in binary.
OK. And let me focus on part of the answer before we introduce what this term is, ASCII. I like your idea of just like a chart. So if we want to represent the letter A, but at the end of the day, all computers can represent is numbers, zeros and ones, or really decimal numbers by turning switches on and off. Well, why don't we all just agree that, you know what, anytime you want to represent the letter A, thank you, with Microsoft Word or Google Docs, why don't we just have the computer store, I don't know, like the number 1. And anytime the computer wants to store the letter B, store the number 2. And C can be the number 3, and so forth. In other words, if we all just agree as humans using these computers to use the same patterns of bits, and bit, if you've ever wondered, is just binary digit. It's a conjunction of the two, bit, binary digit. It's a 0 or 1. If we just agree that all of these can be represented, yes, in switches, in transistors as zeros and ones, well, let's just agree that anytime you're writing an email or a document and you type the letter A, the computer is just going to store the number 1 with some sequence of transistors, and B, the number 2, and so forth. Now, it turns out that's all a computer does, indeed, to store text. But for whatever reason, humans did not choose simple numbers like 1, 2, 3. It turns out that decades ago, humans decided that the letter A shall be 65, B shall be 66, C shall be 67, and so forth. And there's other numbers for things like punctuation and for lowercase letters and a few other symbols you would see on a typical keyboard. And that, indeed, is, as Jaime notes, is a system called ASCII. Happens to be the American Standard Code for Information Interchange. And the American in the acronym there is actually germane because we were a little selfish. We didn't really leave room for things like accented characters or tildes or any number of Asian characters that you might need. ASCII only used 7 bits. So a pattern is 7 light bulbs. And it turns out with 7 light bulbs, you can only count as high as 128, it turns out, if you do out the math. So that means you can have a total of 128 characters in your alphabet, which means there were no accented A's or E's or tildes on ends, let alone various Asian characters. It was, by design, very American-centric. So this was ASCII, but there's something newer that has actually addressed that problem. Does anyone know what that is? There's another term that describes same idea. It's just a different chart, but more inclusive. Felix?
Unicode.
Yeah, so Unicode, if you've ever heard the expression, is sort of one code for everyone, uses either 7 or really 8 bits as needed, or sometimes 16 bits, or sometimes 24 bits, or even sometimes 32 bits. That is a lot of light bulbs to represent letters. And frankly, if you have 32 light bulbs, each of which can be on or off, does anyone want to guess how many possible patterns of light bulbs there are if you have 32 of them total? How high can you count, in other words? I heard billion, so it's actually roughly 4 billion. So if I had 32 light bulbs here, which doesn't seem like a crazy amount, I could actually permute those switches on and off in different patterns in 4 billion different ways, which is to say Unicode has a lot of room for any and all characters. So what are the implications of this? Well, let's just see how this might map. So if the capital A is 65, let's see how we might actually look at an actual word in ASCII. So here's a quick cheat sheet that's a little longer than the one I drew here. A is 65, I is 73, and so forth. Suppose that you received a text message or an email, and if you really looked underneath the hood of the computer, like what pattern of bits is it storing when you got that text message or that email? Suppose that the pattern of bits you received happened to be a bunch of zeros and ones that if you do out the math like we did over here, works out to be the number 72, then the number 73. Yeah, so you literally just got a text message or an email that says HI or hi. And that's why. So your phone or your computer might have gotten, what, 8 or 16 total bits that were on and off in the right patterns to represent the decimal number 72 or 73. And your phone, because it's context sensitive, or your laptop, because it knows you have the text messaging program open or you have your email program open, it's not going to show you zeros and ones. It's not going to show you decimal numbers like in a calculator or spreadsheet. It's going to show you the corresponding ASCII or Unicode letters, which is HI. Question? No? So what if you got like one more character? This one you would have to guess. But suppose that the pattern were 72, 73, 33. Anyone want to guess what message you just got? Hi with a exclamation point. So like hi, this would be in a more excited one. And you wouldn't know this other than by looking it up. And indeed, you can Google ASCII chart or Unicode chart. And you can see the hundreds or thousands of pairings of letters and numbers. But yes, 33 happens to be the number that some Americans years ago decided shall represent an exclamation point. So that's all nice and good. But of course, in the world, we have other letters that we want to represent, not just with these patterns of HI and an exclamation point. What if we want to abstract further on that and actually get more familiar symbols that are all the more common in a language like Spanish, like these, where you want accented characters? Well, that's where you need Unicode, because it turns out you can't cram all of those possible letters into just 7 bits of patterns. So we need Unicode. And it turns out that one of the reasons for this trend these days that I'm sure you have down here are these things called emojis. Right? These look like pictures, but they're not technically pictures. These are characters. These are characters like A and B and C. It's just that they happen to be more graphical. Why? Well, partly because once you have 4 billion possible values for every letter in your alphabet, that frankly just leaves a lot of free room to like be creative. And so humans, every year lately, have been adding more and more symbols to Unicode to represent human emotions and smileys like this and characters and so forth. But they literally are just characters that maybe in the future you could type a smiley face on your computer because it's an actual key. So as an aside, when we talk about Unicode, this is a face with tears of joy. It's apparently, according to Apple at least, the most popular emoji right now. Does anyone want to guess what number is used to represent face with tears of joy? 65, 66, 67 are already taken, so it's some other number. Any guesses? Could be between 33 and 64, if only because those are the only ones we haven't looked at yet. Emojis didn't come out early enough to fit in that range, so they're actually much bigger values. Yeah?
Maybe 500.
Maybe 500, but you'd have to go even further because there's a lot of darn emojis these days, yeah?
I guess you get into territory where you are combining numbers and letters with this. So it would be like 1F602 for that.
That was strangely precise. But yes, perhaps. And indeed, if we actually do this in decimal, if you receive a text message with a face with tears of joy today, your phone or a laptop has just received literally a pattern of bits that represents the number 128,514. Why? just because that one was available. And all of those other variants of smileys are a little bigger than this number and a little smaller, which just means you get a pattern of bits that your phone or your laptop interprets as that smiley face because of the context. If you're in the text messaging program or in your email program, they're displayed as pictures and not as numbers, as they might be if that same pattern of zeros and ones were received in like an Excel file or some calculator type format. It just depends on the context. So any questions then on Unicode or how computers do this mapping? And again, the goal at hand is how do we represent information, inputs and outputs? We did zeros and ones, we did decimal, we did letters and emojis. Yeah?
I guess the question I have is, I know now we know how to represent numbers and letters and whatever, but how do we know, or how does the computer know where a string or a line of number ends and when the other one starts?
Really good question. So computers have generally standardized how many bits it uses at a time to represent information, even if some of those bits are wasted. So in our human world, I could have written not just 1, 2, 3. I could have written 0, 1, 2, 3, or 0, 0, 1, 2, 3, or 0, 0, 0, 1, 2, 3. Those are all the same mathematically, but I just don't because it's stupid, right? Why write numbers that you don't need to? But computers, to avoid the ambiguity that you identify, always use, or almost always use, 8 bits at a time, or 16, or 24, or 32. They use some multiple of 8 typically. And that means that you can distinguish one character's ending from the next character's start by looking at those boundaries. Really good question. Other systems, if you're familiar with Morse code, do not have this feature. And so you can get ambiguous words out of Morse code because sometimes a dot and a dash might actually be a dash and a dot in different contexts depending on where you separate them. Really good question. All right, so we have zeros and ones. Well, actually, at the lowest level, we have like electricity literally coming out of the wall or the floor. Then we have zeros and ones that we can represent by just turning switches on and off. From zeros and ones, we get decimal. And from decimal, we can get to ASCII. So again, these are sort of levels of abstraction. Sort of conceptually, we're working our way up. So we never again have to think about binary, let alone electricity. But what about more interesting aspects of a computer? It's not just text, but what about something like colors? Even if you've never thought about it, you've probably seen this acronym, like red, green, blue is what it denotes in English. And that just refers to a convention, just like ASCII or Unicode, whereby humans use patterns of bits, zeros and ones, to represent colors as well. And they do so by mixing some amount of red, some amount of green, some amount of blue together. And depending on how you mix those 3 colors, you can get any color of the rainbow. You just need to specify how much red or green or blue you actually want. So it turns out that computers typically use 8 bits, which again is a multiple of 8 as I noted, to represent how much red, how much green, how much blue, which is to say 8 plus 8 plus 8, 24 bits are typically used total to represent colors on a screen. So if the smallest number you can represent with 8 bits is, of course, 0, right? All the light bulbs are off. The largest number you can represent with 8 bits happens to be 255, if we did out the math. That just implies that if you want no red, this should be 0. But if you want a lot of red, this should be 255. And same for green and blue. So in that context, if you were to look inside of your computer and discover that your computer is storing 72 amount of red, 73 amount of green, and 33 amount of blue, recall that those same numbers or patterns in the context of a text message or an email might actually represent hi, exclamation point. But if you were to open Photoshop or some graphical program that is supposed to show colors, not letters, any guesses as to what you get by combining like a medium amount of red, a medium amount of green, and just a little bit of blue? And again, the range is from 0 to 255. Anyone want to guess what you get when you combine those colors, Priscilla? Yeah, it's a shade of yellow that looks quite like this here. Why? Well, that's just what happens when you combine those wavelengths of light, essentially. So what does this mean? Well, if you've ever looked really close on your computer screen or even a flat screen TV, you might have seen actual dots. Like things get kind of splotchy the closer your human eyes get. What are those things called that you're looking at, the dots? Yeah, they're called pixels. And they literally are just dots on the screen. Your TV, your phone, your laptop is just thousands of tiny little dots, little squares. Each of those squares, typically in a computer, is represented with a pattern of 24 bits. 8 showing how much red, 8 showing how much green, 8 showing how much blue. And so if you think of those 3 colors, red, green, blue, just overlapping, you get a single dot like this that represents 24 bits. So if you've ever looked or cared how big your photographs are when you're storing them on your laptop or your phone or any of your file sizes, those file sizes are measured not in bits, but what units of measure? Yeah, so megabytes maybe, or kilobytes, or gigabytes if it's a video file. Well, a byte, B-Y-T-E, is just 8 bits. Why? Well, 1 bit is generally pretty useless. You can only count as high as 1. So units of 8 were common there too. So 8 bits is 1 byte. 1 megabyte is 1 million bytes, which is to say that if you have a lot of these little dots, each of which takes up 8 plus 8 plus 8, or 3 bytes, you can literally do out the math and figure out how big your photograph might be. Because if you know it's this many pixels wide and this many pixels tall, and each of those dots takes up 3 bytes, 8 bits plus 8 bits plus 8 bits for red, green, blue, you can literally do out the math and say, oh, this photograph's going to be 3 megabytes because of that simple math. So even though these file sizes might seem completely arbitrary, they can be mapped directly to this kind of math. Now, as a side, computers are smart these days. They compress files to save space, so it's not quite as simple as that. But as an upper bound, it indeed is. And we can see this even in this emoji. Right? If we start zooming in digitally on this, we can start to see these pixels. And if we go really close to his eyes, you'll see these squares, which are indeed just dots. And so there's different colors here. Like each of these yellow dots is represented with one pattern. This shade of black is represented with one other pattern. And these shades of gray are slightly different patterns. But that's all they are, is bits. And in the context of a graphics program like Photoshop, your computer will show you them as such. All right, so we've got electricity, zeros and ones. Decimal, ASCII, or Unicode, now colors, now images, because an image is just a whole bunch of colors, left to right, top to bottom. What comes next? Yeah, so what's a video? What's a movie file? Yeah, it's a representation of multiple pictures, right, that just fly across the screen really fast, creating the illusion or tricking our human brains into thinking there's actual motion. If you grew up with one of those little paper flip books, little cartoons, and you flip them really fast, it looks like some cartoon is being animated, but no, your brain is just kind of interpolating, so to speak. It's interpreting all that motion, those changes as movement, even though every picture is actually stationary. So if you've ever heard that a Hollywood movie is 24 frames per second or 30 frames per second, which are common units of measure, that just means you are being shown by some producer 24 pictures per second or 30 pictures per second, which are probably slightly different from each other, thereby creating the illusion of movement. So now we're all the way at the top of the sort of abstraction layer here, whereby now we have videos, and we started with like the most mundane of details. And that really is what computer science is about too. Not just representing information, but sort of solving a problem at this level, using it as the input to another problem, using that as the input to another problem. So now we're having kind of a cool conversation about video files when at the end of the day, we just started with like electricity coming out of the wall. So that principle of abstraction is inherent in computer science. And this is kind of the thing you learn when taking a class like that. And these animojis that you have, if you have an iPhone, for instance, silly little video files that track your face these days, they're just sequences of images being shown to you pretty quickly, looping no less. And that's all an image or a video file like this might be. All right, so that's 2 out of our 3 topics, inputs and outputs. We just need this thing in the middle. But before we forge ahead, any questions or confusions? Yeah, Carlos.
So I'm assuming sound is going to be similar, right?
Yes, so sound is also similar, where you'll typically measure like the frequency of a sound wave, so how quickly it's going up and down, and also the wavelength, both of which can really be encoded as numbers as well. As ones and zeros, indeed. Indeed. And back, was there a question? No? Daniel?
How does the computer know that a pixel is a square?
How does the computer know that a pixel is a square? Technically, it doesn't. It's just hardware devices have decided that pixels shall be squares. And so therefore, when you store an image, you should assume that every dot is same height as it is width.
Okay.
Yeah?
Today we are working with binary, but there is another trend that is qubits.
Yes.
Quantum processors. So I want to know if the binary and the qubits will be coexist.
Good question.
How they work, and what would be the future to our devices.
Okay, so some of that I can answer. The rest we'll have to wait and see. So for those unfamiliar, qubit is kind of a cute word that refers to a bit in quantum computing. Quantum computing, or qubits, essentially refers to an envisioned technology on which research is being done, where technically you can have a device like a light bulb that's in both the on and the off state at the same time in some weird way. It really derives from physics. And so with qubits, you have the ability at first glance to store more than just a single bit of information. You can store a qubit, which is more in the sense that it can be in two states at once. This is dangerous theoretically because a lot of the world's security these days relies on cryptography, the art of encrypting or scrambling information. And a lot of encryption relies on the perceived difficulty of solving certain mathematical problems quickly. For instance, it is really hard to take a really big number and factor it. That is, break it down into two smaller numbers that, if multiplied together, give you that big number. But with quantum computing and qubits, if you have the ability to essentially be in multiple states at a time and therefore do multiple types of work simultaneously, the presumption is that that is bad for things like cryptography because you could solve problems much more quickly. Now, how soon that's going to happen or if it's going to happen, that I don't know. For that, take your INCAE's course on quantum computing, perhaps. But that's a whole field of research unto itself. So let's look now into this black box, literally. So in between your inputs and outputs is like the real intellectual property, the secret sauce via which you want to solve problems. And those are generally called algorithms. An algorithm is just step-by-step instructions for solving a problem. It's kind of a nice fancy word, but it really is just that. It's like a list of commands or instructions that you feed to a human or to a robot or to a computer. So what's one such algorithm? Well, back in the day, we, like you, used this technology here, phone books, in which you have lots of names and numbers. And the names are hopefully sorted from A to Z. And the numbers then line up with the individual's names. And so if I wanted to look up a friend or a colleague's phone number, I could just look up that number and then call them. So I don't know why I'm explaining how a phone book works, but it's very similar to this technology now. In fact, even though we don't really use these devices anymore, it's the same problem, right? You probably have an icon on your phone, iPhone or Android, that is your contacts, and they're just sorted alphabetically top to bottom. But if you type searching at the top and you start typing like DA for David or JO for Jose, you'd like to think that it jumps right to that result. That's the same problem. It's just the software is jumping to Jose or to David's name very quickly. But how is your phone doing that? Or how would we humans do it back in the day? Well, this is a problem to be solved, and the input is this physical book. And so maybe I'll start at the beginning and look at one page, and I look down. And maybe I'm looking for my friend Mike Smith, last name S-M-I-T-H, so Smith. So if I just look at each page, I'm not seeing him yet. But this is an algorithm. For each page, look down, and if Mike's there, call him. Otherwise, move to the next page. And we wouldn't even think about it. You would just do it. Is this algorithm, this step-by-step process, correct? Yeah, I mean, if Mike is here, we'll find him, but what's the catch? It's going to take forever. I mean, this is a stupid algorithm, but it's correct, right? If Mike is in this phone book, I will eventually find him probably way back here. So what would be slightly smarter? Well, let me just do 2, 4, 6, 8, 10, 12. It's hard to do physically, but it does sound like it's going twice as fast. Is that algorithm correct?
No.
OK, why? Yeah. Yeah, so I could get unlucky and maybe he gets sandwiched in between two pages and I just miss him altogether and I conclude, no, there's no Mike Smith here. Now I could fix that bug, that mistake, and for instance, if I hit the T section, name starting with T, or SN instead of SM, I could maybe double back a page or two, and that's not very expensive. It doesn't take me a huge amount of time and I can fix that bug. But it would be roughly twice as fast. But no one's going to do that either. What's any human going to do? Yeah, I heard go open to like the middle. All right, I look down. I'm in the M section. So Smith is this way. So what do I do next? Yeah, so I repeat, but I could more dramatically like tear the problem in half, throw half of the problem away, and now I'm left with same problem. Where's Mike Smith? But it's half as big. So I hope that's socially acceptable to tear phone books in Costa Rica, because we do this all the time in the US. But these are hard to find too, though. So Mike Smith is somewhere in this phone book. Where is he? Well, let me just go roughly to like the middle. And I look down. Oh, I went a little too far. T section now. But now I know that Mike is not in this half of the phone book. And so I can tear that half of the problem away. And what's compelling here is whereas that first algorithm was very lazily going 1, 2, 3, or maybe 2, 4, 6. If I started with like 1,000 pages in this pretty thick phone book, I just went from 1,000 to 500 to 250. I'm really taking big bites out of this problem. And if I just repeat that same algorithm again and again, I'll probably be left ultimately with just one page that Mike is either on or not. So just as an aside, suppose that phone book did have like 1,000 pages. How many times might I have to turn it to find Mike Smith the first way? One page at a time. Yeah, like 700, worst case 1,000, but like, 700 because it's, it's more than halfway through. What about the third algorithm where I divided and conquered, so to speak, splitting it in half every time? Yeah, 8 or 9, even fewer. A little more. It's probably 8 or 9, maybe 10, depending on how we round. But yeah, if you start with 1,000 pages and do the math, you go from 1,000 to 500 to 250 to 125 and so forth. You can only have 1,000 roughly 10 times, depending on how you round. So that's pretty powerful. It might take me 700 steps to find Mike Smith in the first algorithm, but my God, like 10 steps in the third algorithm with the same inputs and outputs. So computer science 2 is all about just kind of harnessing, frankly, our human intuition and expressing ourselves a little more carefully, putting a little more thought into the problem, and then getting much, much faster or more efficient results. And so how might we then quantify this difference? We don't have to even talk numbers very specifically, but if this is just a chart, and here is the size of the problem. So this is like number of pages. So a lot of pages over here, few pages over here, right to left. Vertical axis, time to solve. So maybe 0 seconds and a lot of seconds could be our unit of measure. The first algorithm is really just a straight line. Why? Because if the phone company adds one more page to the phone book next year, that just means it's going to take me one more page turn or one more unit of time. So it's a slope of 1, if you will. The second algorithm is going to be the same shape. It's a straight line, but it's lower. Because if the phone book has this many pages, the first algorithm might take me this many steps, but the other algorithm, where I'm going 2 pages at a time, takes half as many steps. So the line is the same shape, but it's just lower on the chart. The third algorithm, though, is fundamentally better, and it's a logarithmic curve, if you will. And even if a little rusty on what a logarithm is, it's a curve that looks like this. It's always increasing, but it increases more slowly and slowly and slowly. The implication is that suppose that the phone company next year like doubled the number of pages in the phone book. Well, how many more steps would the first algorithm take if you went from 1,000 pages to 2,000? Like another 1,000 steps, right? Like Mike might be 1,400 pages in, twice as far in if the phone book is twice as big. But no big deal for the third algorithm. If the phone company doubles the size of the phone book because maybe 2 towns combine phone books, how many more steps will it take to find Mike Smith next year? Just 1, right? No big deal. Tear it in half one more time. And so algorithms, when you think about the efficiency and when software engineers sort of compare the efficiency of their code and try to claim that our product is better, our product is faster, you can absolutely just measure it by counting seconds on a clock, but you can also make more theoretically sound arguments and say, well, our algorithm is fundamentally better than yours because look, as n gets large, where n is just the number of pages in the phone book, it barely takes us any more time. And so it's the Facebooks of the world and the Googles of the world that really care about getting algorithms not just correct, but efficient so as to leverage those kinds of implications. And Oracle and any database company is similarly trying to invent algorithms like that. Any questions there? All right, well, let's formalize that. All of us just kind of intuited that a moment ago, but let's introduce one language today. And for more languages, you can take CS50 at INCAE with Jose and Jaime and team next term and beyond. But pseudocode is not an actual language. It's like a language-like syntax. Most people write it in English. You can write it in any spoken language, though. And it's just meant to be short, succinct instructions that get your idea across to another human before you write actual code. And here is how we might write the pseudocode for that algorithm to find Mike Smith, where I divided and conquered. Step 0 was pick up the phone book. Step 1, open to the middle of the phone book. Step 2, look at the names, and then I make a decision. If Smith is among the names that I'm looking at, then I'm going to go ahead and call Mike. But that's not the only possibility. It might be the case that, Smith is earlier in the book, in which case I should open to the middle of the left half of the book. And then, frankly, just go back to step 2, because I already have the same logic ready to go. Else, if Mike is later in the book, open to the middle of the right half of the book, and then also go back to step 2. Else quit, because Mike presumably is not in the book. If he's not there or to the left or to the right, it must be he's just not in the phone book. So what are the characteristics of this program? Well, in languages like Java and C++ and others, you see commonalities. So this is just pseudocode, but everything I've highlighted in yellow here in a proper programming language like Python is going to be called a function. And a function is just like a verb, an action that the program or the robot or the human can take. Here we have conditions or decisions that the computer can make. If this, go that direction, else maybe go this way. It's like a fork in the road, and you have to decide which branch to go down. These things, a little more technically, are called Boolean expressions after a mathematician named Boole. And a Boolean expression is just a question that has a yes or no answer, or a true or false answer, or more simply, a 1 or 0 answer. Ones and zeros are just really nice when you want to represent two opposing ideas, true and false, yes or no, or some other idea. So a Boolean expression is just going to say yes or no. So Smith is later in the book, it's a question, or is Smith earlier in the book, also a question. And then lastly, we have this. How might you describe this yellow feature now? Yeah, it's some kind of loop or cycle. Now, this seems a little dangerous because if I keep going back to step 2, this would just seem to go forever. But that's not going to be the case because according to the third algorithm, what did I also do every time I repeated myself? Yeah, I looked at only half of the problem, right? I literally split the problem in half. So it was this big, then this big, then this big. So it's fine if I keep doing the same thing again and again, because eventually I'm going to end up with one page, and then Mike's either going to be among the names there, or he's not, at which point I can quit. So that's what's called recursion, doing something again and again, but making the problem smaller each and every time. So we thought then we'd conclude with a final demonstration that is sort of a pop quiz of sorts here, especially for those of you who came into today less comfortable. We thought we'd make an algorithm together. Could we get perhaps 2 volunteers to come on up? 2 volunteers. 2 volunteers. Let me just give folks a moment to get comfortable with the idea of coming on down. 2 volunteers. You can maybe nudge the person next to you. Or you. Oh, wait, you made eye contact. Can I call on you? What's your name? Carla? OK, Carla, come on down. You made eye contact. Carlos, you want to come on down too? And I think I saw Jose's hand, if Jose would like to come up too. Come on down. Jose, why don't you hop in the middle here? Carla and Carlos. Nice to meet you both. So thanks to the team here, we brought some food for at least 3 of us. All right, here we go. And you'll see that we have a knife for each of these participants. And a very common algorithm back home is the act of making a sandwich. And in fact, one of the first things I learned in 5th grade, so really young as a kid, was how to, or really how not to make a peanut butter and jelly sandwich. But of course, all of you have done this or some similar sandwich that you might like here locally. Peanut butter and jelly is very common in Cambridge. But we have all of the ingredients for this. So the challenge at hand is quite simply going to be to program, all 3 of you, to make us a correct peanut butter and jelly sandwich. So if you're thinking, boy, this is easy, that's great, because it's going to be all of you dictating the instructions. So here we have the last ingredient. All right. So shall we begin? Who would like to offer step 0, so to speak, our very first step to make a peanut butter and jelly sandwich? And for those unfamiliar with this tradition in the US, it's a piece of bread, jelly, and peanut butter together in sandwich form. That's not an algorithm, though. OK, right here in the middle. Pick up bread. All right, Priscilla, step next.
Open the bread.
Open the bread. Thank you, Carla. All right. Nice. All right. Next step, Alejandro.
Okay, it should be open back, right? Because the professor did what Priscilla said. No, but
It said open the bread, so I think that's ambiguous. Is the real takeaway here?
Okay, step 3 will be that take 1 slice of bread.
Okay, step 3. Take 1 slice of bread. Carla, how dare you? Getting ahead of us. Okay. Okay, next step. I think I hear something here. Put the bread on the dish. Thank you, Carlos. Next step, someone over here. Is Javier? Open the peanut butter. Interpret as you will. Take covering off, I heard. I think that was Carla's inclination here too. Good. So we're getting a little better at what it means to open. Sure.
Grab a knife.
Grab a knife. That sounds safe. Okay. By the handle, I heard. Thank you. Next step. Yeah. Put knife into the jar. Okay, next. And scoop. Whatever you want, okay. On the bread. Okay. All right, next step. Next step. Yeah, over here.
Spread the peanut butter.
Spread the peanut butter using your right hand, it seems. Evenly. On the bread. And did I see a hand here? Next step. Yeah, over here. Put the bread on the dish. Take another piece of bread. No, no. Okay, open the jelly. Next step. Remove the security seal, if any. And now let's go somewhere else. Next step. Next step. I heard right here. What would you like them to do? Put the knife into the jelly. Okay. Okay. Next step, almost there, yeah? Maybe if it's a jar. Okay. Okay, if it's a jar, scoop it.
On the bread.
Thank you, on the bread. Very nice condition, as we called it. Other steps, almost there. Spread, I heard. Spread the jelly with also the right hand again, it seems. On the bread. Pick up bread. Okay, and we're almost there. Combine bread and?
Grab another slice of bread.
Okay, grab another slice of bread and? Combine it. Put it over the other one. And I think a big round of applause for our volunteers, if we could. So that then is computational thinking. If you're not graduating quite soon, allow me to encourage you to take Jose and Jaime's class, CS50 at INCAE. It's been a pleasure being here, and I'm happy to stick around one-on-one for questions. Thank you all so much.